Coming. So my name is Andy Saru, and I'm from Datomi, which is a Chicago-based company, and I'm here to talk about building a large-scale, real-world system on open-source technologies. So just a little bit of an overview of the agenda. I'm going to start with a few things about our company and what we do, and why we chose open source or chose an open source strategy. And then I'm going to go through some of the basic principles that we followed for building a large scalable system. And I'll talk a little bit about the open source technologies and where they fit into that. And then I'll kind of wrap up with an overview of our system and the actual tools that we use. And then I'll open it up for questions. Okay, so just a few things about the company that I'm coming from. So Datomi is an advertiser, or is a digital advertiser. We're in the banner ad space. So we, we're behind a lot of the banner ads that you see. We're kind of one of the sort of infrastructure of the internet kind of companies. You may not have heard of us, but almost certainly every one of you has seen one of our ads at some point. We work with like 40 of the top 100 retailers or e-tailers, and we serve primarily targeted and very customized banner ads. So some stats. At peak, we're doing about 2 billion bid requests a day. So a bid request is a certain kind of advertising setup where the content providers are able to open up a slot for a banner ad to multiple advertisers who will all be able to bid on it in real time. It's called real-time bidding. So at least the way that we bid, we're lucky if we win 10% of the bids that we place. So we do at least an order of magnitude more bids than actual banner ads served. But of that, at peak, we're doing about 100 million banner ads per day. So to accomplish that, we've got a little over 500 Linux servers and spread across 3 data centers. And we're in essentially a pure open source environment. So our ad server doesn't have any licensed technology in it whatsoever. And so we are made up of about 25 or so developers, mostly doing Java programming. So, so you can probably guess that some of the major challenges that we face to hit that kind of scale is, well, just scalability in general. How do you build a system that can take that many requests and handle them gracefully? But one of the biggest issues is the low latency requirements. So in a bidding environment like ours, you get a very short amount of time to enter a bid before you get cut off. So the way the networks work is they'll broadcast bid requests to maybe a half dozen or so different advertisers that they'll select in real time. So the user is sitting there waiting for their page to load, and all of this activity is going on behind the scenes. So because there's multiple round trips involved, each round trip has to be extremely fast. And the cutoff times will range from 80 to maybe 120 or so milliseconds. But if you are getting a bid request in Chicago that originated in New York or California, you can expect about 50 milliseconds of that is going to get eaten up just in internet latency. And if you're going coast to coast, it's over 80 milliseconds. So obviously, if you need to hit an 80 millisecond average and you've got 80 milliseconds in network time, you're not going to win very many times. So we have to have. This is why we have two data centers, one on each coast. But even with 2 data centers, if you're about half the country away, you're looking at 40 to 50 milliseconds average latency. So that means that our internal time generally has to hit around 20 milliseconds, which is not a lot of time to do a whole lot. So speed is extremely important, caching is extremely important, and optimization is important. A couple other challenges we have is interoperability. So every ad network has a different protocol that they make up their own. There's no standard whatsoever. Some of them are sending us protocol buffers. Some of us are sending XML or JSON, and sometimes it's just raw HTTP. So we have to be able to work with any network's protocol, and we have to be able to change our front-end protocol to match theirs, with a moment's notice, because they're constantly changing. And then the final big technical challenge is just maintainability. So we have a very large code base. Last time I looked, it was around 1.5 million lines of code, which is, for a group of 25 people, is a fairly large project. So why did Datomi choose open source? Because there were a few other options. We looked at solving part of our problem with Terracotta, which is a kind of a big data company, and they sell different solutions for caching and persistence. But for various reasons, it just didn't fit for us. And so I've named kind of the top 4 reasons that we went the route that we did, in order of importance. And the most important one is agility. So with any licensed technology, you have to deal with just the round trip of getting a salesperson in, doing a technical evaluation, appropriating the budget, negotiating the deal, and in my experience, you're looking at least 4 to 6 months for every technology that you choose. No way that we could work that slowly. And some of the bigger issues is you really have to do a lot of trial and error when you're working with large systems like ours. No matter how scalable a product is, it only really scales if you use it just right. And you don't know if you're using it just right half the time until you actually throw it out into production and see what it does. So you can't go out and spend a bunch of money on some technology and then find out after 3-4 months worth of integration work that it's not going to work and have to change your mind. With open source stuff, you can change your mind as rapidly as you want, and you can swap out modules and play with different techniques. Some things that we've done is we've run 2, sometimes 3 different options simultaneously, and we'll take a mod of the key, for example, to send a third of traffic through this library, a third through this one, and a third through this one, so that we can get very good comparative numbers. So then the second most important requirement is visibility. And this one is fairly obvious. So the open source tools that we use, obviously, we've got the source code so we can see what's going on. But you also have visibility into the process, the development process, because you communicate with the developers, very easily, and you can actually, commit your own changes. You can make your own changes if you need to. That is extremely important in a large-scale system because, like I said, they're not very predictable. If you have something that scales very well in one direction, but it's not working right in your setup, you really need to be able to get into that code to figure out why it's not working the way that it is, or that you expect. Now the third reason is fit. This just plain and simple is you can choose the right tool for the job. With open source technologies, usually you have 10, 15 times as many options as you do with commercial technologies. So you have a much higher chance of finding exactly the right kind of tool that you need. And then finally, maintainability. And this is this again goes to you know, being able to have access to the source code. You always have the option of maintaining the code yourself, which you don't have to worry about companies going out of business. If the open source project is abandoned, you know, you still have the source and you have it in your possession, and you can maintain it if you need to. So just kind of a quick quick preview of some of the stuff that we use. This is probably maybe, I don't know, what would you say, David, about a third of what we actually use? Okay, I must have a thing to stay on. Yeah, so the big ones are obviously our web servers. Yeah, I didn't mention Linux. That's a good point. Didn't even think to put that on there. But our web servers, some of our backend stuff, Memcached, HBase, JMS, Cassandra. You know, these are all things that you know, that we're actively using. Okay, so I'd like to jump into you know, 4 of the key principles that that I've identified, you know, just in my experience, for putting together big systems. Keeping it simple, divide and conquer, monitoring, and automation. So let me skip ahead a little bit. So first principle, keeping it simple. There's basically you know, 2 points to this. The first one is complicated code is almost always slow code. So you know, by keeping it simple, you know, just the fact that you have less code, it's probably 9 times out of 10 going to run faster than a more complicated system. But perhaps a more important aspect of that is simple code is code that you know how it works and you know how to use it correctly. You know, so if you have a good intuitive grasp of the software that you're operating, there's a much better chance that you're going to be able to extract the best performance from that. You know, if you contrast that with a, you know, sort of overly complicated general purpose library, you're less likely to be using it, you know, at its optimal. You know, so as I've noticed, you know, misusing a tool is potentially the easiest way to kill your performance. You know, for a number of reasons. You know, often you'll pick up a library that you know, somebody has benchmarked. You find benchmarks on the internet all the time, which are, you know, not exactly the most valid. But very often these benchmarks are using a tool in a very, very specific configuration, and they'll compare it against something else that you know, has sort of a generic configuration. So it is theoretically possible to get those kinds of numbers out of it, but if you don't know how to get those numbers out of it, there's a good chance that you won't. And when you don't, the performance is often extremely bad, not just a little bit slow, but prohibitively slow.
Just described there by one of Andy's colleagues, would what happened to us the other day be an example of misusing a tool? And would that be a worthwhile thing?
Yeah, I wasn't going to bring it up, but
no.
Yeah, so this actually happened just a few days ago. We put out a release where we had swapped EHCache out for some Guava caches, which is a library that Google open sourced. And you know, there's a couple different methods. You know, like most libraries, there's more than one way to do the same thing. And the method that we were using for removing items or expiring items from the cache was you know, like 1,000 times slower than the equivalent method in the EHCache side. So we put this out, and you the performance was a little funny. It actually ran okay for, for 20 minutes or so, but then performance actually started to degrade. And after about 3 hours or so, it was so bad that the servers had to be restarted. And it turns out the reason was that it would
Two.
went great. All right. So yes, that is a very good example. Okay, so kind of on a related note, the second principle is using the right tool for the job, and this is perhaps the #1 reason why I like to use open source stuff, because you have so many options. You can always find something that is just the right fit for what you're trying to do. But the other aspect of that is people who write open source software are people who are in, or were in the same situation that you're in, and they are writing a tool to solve their problem. They're not writing a tool that they're trying to, to market, and they're not trying to solve, all of the world's problems at once. They have a very specific problem. They write the code that solves that problem, and then they say, you know what, I'm going to open source it. So they put it out there. Again, in line with keeping it simple, you've got a very specific library or a very specific server that does just the right thing. So one of the things I like to do is favor an a la carte approach to designing systems. This is in contrast to using big frameworks. So big frameworks, they try to be everything to everyone, and it's very difficult to get good performance in every aspect because they have to consider so many different options. If you have a specific library, it's much more likely to perform well. Another reason that I would say you want to follow an a la carte approach is that if you have a framework or one solution that tries to do 5 different things or solve 5 of your problems, you're kind of locked into using all 5 of those pieces. Either that or you're going to drag around a lot of unnecessary bloat. All 5 of those things may not be the perfect fit for what you're trying to do. Whereas if you had, 5 different tools that did only one thing, you can swap, any one of those out independently. It kind of goes to, the core software engineering principle of loose coupling. If you're using a big framework, all of those things are coupled. They're tightly coupled. You get them all together, and you take it or leave it. That is not always the best for you as a software engineer when you're designing, for scalability. And then the last bullet is you want to solve the problem that you have, not problems that you don't. I hear this from a lot of people. They're comparing different solutions when you're, evaluating software or something, and they'll say, such and such is better than that because it does all of these things, and that one doesn't do that. That's all great, and if you were actually paying for the software, that might actually be a valid point. But if you're not paying for it, you really don't care about what that tool does that you are not actually going to use. So, quite often the best choice for you is going to be, something that has a very narrow feature set. So a couple examples or tips, I guess. One of the hottest philosophies right now around scalability is NoSQL. That's a perfect example. So you can use a regular relational database to do anything that you can do with a NoSQL database. And NoSQL has a very limited feature set. It does not do a whole lot, You can get things by key and you can store things by key, but that's about it. You really can't do queries across a range of keys or anything. But it turns out that those new NoSQL solutions are almost always going to perform better than a relational database. And the one feature that they do give you over a relational database is that they're very easy to scale. Because they're already partitioned and because your interface is so narrow, it's very easy to add new nodes to your cluster. Rebalancing data is not terribly difficult, and just all in all, it gives you a much simpler solution. So the biggest thing that you want, and if your problem that you're trying to solve is you have keys and you want to get things by key and you want to store things by key, the NoSQL solution gives you the fastest possible read and write performance. And you lose all of the rest of it, but you don't need that stuff anyway. Another example, using the right tool for the job, something that we do is we use Memcached for our memory cache. That gives us very fast reads. Reads generally have to be synchronous because you've got somebody waiting to use the data. But writes do not need to be synchronous. They can be done asynchronously. We have this sort of asymmetric solution where we do all of our reading from Memcached, but our writes actually go through JMS. You've got basically two solutions in place of one, but it turns out that you actually get much better performance, and the design is a lot easier to work with. Yeah, you have two very different patterns. Yeah, I mean there really is no single solution that I can think of that that really solves that problem. Where I want my reads to be super fast, but my writes they can be done different. Okay. Third principle, divide and conquer. So this is kind of an obvious one, but anytime you're trying to scale up, you're going to have to partition at some point. And partitioning for the very large solutions is not just about partitioning data, but you're partitioning everything. So you're partitioning the requests, and you're partitioning the the different kinds of data that you have in your system. They all have to be sort of partitioned the same. So one of the things that we followed is we partition every piece of data that we have, even if we don't need to. We have certain data sets that in theory you could fit on one big server, but we don't. We shard it because well, for one, you don't know how long you're going to be able to fit it on one server. But also you have single point of failure if you're putting it on one server. And the basic paradigm is just different. You've got kind of a star pattern instead of a mesh or really sort of a silo. What you want your system to look like, or what you want the flow of request traffic to look like, is everything should kind of be vertical. So you have two requests coming in that have different keys. They should not really touch the same server at any time. They just kind of go right through. And then you have a bunch of parallel lines. If you have everything coming in a star, then there's no way you're going to avoid having a bottleneck at some point. Right. Yeah, absolutely, absolutely. So what you want to do is you want to co-locate objects that have the same key. So, for example, if you're dealing with 3 different bits of data, but they're all sort of keyed by a user ID, all of that data for one user should live in the same server. and you want to move the process to the data. So that means you're not going to load balance across a bunch of ad servers and then have each one access a database, to load the user, because then you can't really cache very effectively. If instead you shard the ad servers, which is what we do, and you say that this ad server is going to handle this group of user IDs, and this one's going to handle this group of user IDs, and so on and so forth, then it becomes very easy to use an L1 cache, because they're all going to have the same data. And for any bit of data, you know exactly what web server it's going to go to. Another reason is just for basic troubleshooting. It's very, very difficult to troubleshoot a server that's going to be load balanced across multiple tiers, because you don't know where any one request is going to land. And if you've got hundreds of servers and you're trying to trace, one user request, good luck. Good luck finding that. Another tip: resist the urge to replicate data. Data replication is about the most painful thing you can have to go through in a large-scale system. I've done it a few times. At some point in your life, you are probably going to have to replicate data, but you should do it kicking and screaming. You should always try to find a way around it if you can. So one of the things that you can do is you can duplicate read-only data. So this essentially allows you to shard in situations where you might not otherwise have been able to. So for example, let's say that you have some company-level data and you have some user-level data. Usually if you're serving a request for a particular user, you're not going to have to change any company-level data, but you will need to use it. So you copy the company data across all of the ad servers, but you shard the user data. Okay. Principle 4. Monitor, monitor, monitor. So monitoring your large system is every bit as important as testing the code that goes into it. In fact, I would almost say that it's more important. A couple of basic reasons. Well, testing. I think some of the stats that that I've seen, I don't know how realistic they are, but at some point somebody did a study and said that roughly 25% of bugs can be identified through testing. They said in the study I was reading that 60% can be identified via code review. But 100% of them can be identified by putting the code out into production and seeing what breaks. That's not always an acceptable way of doing things, but since it does work, it would be very foolish for you to do that and then not actually be watching to see what breaks. So extremely important to have your monitoring in place. Another reason that I stress it is that if you've got one or two servers and each server does one thing, monitoring is fairly straightforward. When you have several hundred or even thousands of servers, monitoring is actually a pretty interesting technical challenge. But it is something that people have solved, and there are tools out there for it. Did you want to? Yeah. Yeah. It's I would hesitate to say that it's completely impossible, because often it is in theory possible, but it's often impractical. So you want to monitor at multiple levels, and I've identified 3 three main ones. The basic ones are your obvious OS level checks. You want to make sure that your operating system is good. You want to make sure the server's running. But you want to look at your operating system memory, CPU utilization, basic I/O stats. There are a lot of tools out there for doing this. Two that we use, and two of the better ones or more popular ones are Nagios, or some people say Nagios, and Cacti. So Nagios is mostly about checking particular stat points and alerting if they exceed or go above or below configured thresholds. The way we have it set up, we send emails and SMS messages to the relevant parties if any threshold is exceeded. Cacti, on the other hand, is about charting. So it will chart your CPU utilization over time. Your memory utilization, and you can set it up in theory to chart just about anything. But these particular tools tend to be best for for fairly low-level checks. So one level above the OS is sort of your application level stuff. And there's a tool that we've just started using called OpenNMS, which we're actually going to be replacing Nagios and Cacti with OpenNMS because it has kind of a redundant feature set. But these are things that are specific to your the process that your application is running in. So, for example, your Java heap space, anything that you can expose via JMX, MBeans, you can use OpenNMS to do. And it works fairly well out of the box, provided that you follow certain conventions. But then the third level is, perhaps one of the more interesting ones. And for lack of a better term, I've called these your stakeholder metrics. But these are the things that are very specific to your application. They're business level things. Your requests per second. What is the value of your request? If you're working on a trading system, for example, you may want to know, how much money have you won or have you made or lost, in the last 60 seconds or something. A few of the things that we're interested in is traffic per company. So just looking at the overall request per second of one ad server is not interesting to most of our stakeholders. They want to see how many requests are their companies, receiving. So that kind of stuff requires a lot of custom work, obviously, and custom stats. For that, we've started using a tool called OpenTSDB, which is a time series database, and it charts, fairly real-time data. Obviously, not immediate, but we've got it running at about 5-minute checks. We could also set it to 1 minute. But it gives you pretty quick feedback on whatever metric you put in place. But it's backed by HBase, which is in itself backed by Hadoop. So it scales very well. If you need to put in more stat points than one server can handle, then you add another one or another one or another one. We've got it running across 3 nodes right now, and it's performing fairly well. But this thing is taking billions of stat points and aggregating them and presenting them in real time. And you can define whatever stat points you want and get them in the system pretty quickly. So a couple tips that we've used for for working in these kinds of systems regarding monitoring. The first one is you want to designate a staging server. So this is about monitoring the performance of new code and comparing it to the performance of old code. This is very similar to testing, and it's kind of like part of our testing continuum, where we do our continuous integration, we do our unit testing, we do our automated functional testing, but then the last bit is we're actually going to put this out onto one real production server and start piping real production traffic through it. And this is actually an extremely useful capability. And when you've got 500 servers to work with, and each one is taking 1/2 of 1% of your traffic, you can actually blow 0.5% for a few hours without taking a whole lot of damage, and you can see what happens. And keep in mind this has already gone through QA, but like I said, you've still got 75% of the bugs still left to find. Very, very useful to be able to take live traffic, a very small portion of live traffic, and push it through the new code. And via monitoring, because you know what you're looking for, you can really find those defects quickly. And it's orders of magnitude faster than trying to reproduce this in a test environment, or even replaying production traffic is of limited use, and just is not as good as sending real traffic through it. Well, that's interesting that you would say that. So, staging server is is sort of one side of it. Then the opposite side is what I call a canary. Sometimes people refer to the staging servers as canaries, but I think the metaphor is more appropriate in the opposite case. So we use canaries in our ad server, which is a server. We have one per data center that takes 25% more traffic than the rest. So we deliberately overload one server. And the purpose of this is to find performance issues, or to give us sort of an early warning. The metaphor is the canary in the coal mine, if anyone's not picking that up. So the canary in a coal mine, miners will bring a canary in with them, and if the canary dies, they know that there's toxic fumes and they should get out. But the point is the canary is going to die before any people do, so they can get out in time. In our example, that overloaded server, if there are any capacity issues that you're about to hit, you're going to have one server is going to go down, but you still have a 25% buffer before the rest of them go down, and you can take the appropriate actions, and hopefully you have enough time to actually requisition hardware or whatever. We started doing this because we found that capacity issues are very non-linear. So if you're just looking at memory use, CPU load, I/O, all of the basic things, they don't sort of go up like this with load. They will flatline or kind of plateau, and then they'll just hit the wall very often. And you don't know if you're a mile from the wall or 3 feet from the wall often. So the canary really does that for us. So when the canary croaks, you know that you need to back off or add some hardware fairly quickly. Okay, so enough with the principles. So this is our basic outline of what our web server looks like and the different things that we've used. So starting from the top, our web servers are Apache and Apache Tomcat. We have a very simple API. We just serve banner ads. We don't have a whole lot of rich content. We don't use servlets a lot. But we found that Tomcat actually performs the best of all of the Java-based web servers. So you can compare it to Jetty, for example, which would be a much lighter weight framework. But Tomcat will actually outperform it by a bit. So, David, that's your area. Do you want to comment on that at all? Mm-hmm. Yeah, that's a good point. I didn't think of that. Yeah, so Tomcat, I think, kind of goes a little bit against my point about avoiding frameworks, because Tomcat is actually a fairly heavy thing for what we use it for. But like I said, it's just turns out that it was the fastest. We don't use 98% of it. We just use it to execute some Java code and do threading appropriately. So one tier below the web servers is what we call the ad server. Right. Right, yeah, so that's a good point. So the incoming traffic to our web server is HTTP, and it is load balanced. So you can't avoid load balancing when you're taking arbitrary HTTP traffic, because you don't know what the user identifier is going to be. You could, I suppose, shard on IP address or something, which is something that I think LVS supports. Right, so you can take certain ranges of IP address and send them a certain way, but that's not usually very useful. Because you don't store your data by IP address? Well, yeah, all right. In general, your big data, you don't. Yeah. Mm-hmm. Yeah, I'm pretty sure it does. It's basically stickiness, right? Yeah. So, I mean, like I said, load balancing is something that we try to get past fairly quickly. So, kind of the way I think of our web servers is they're sort of business-specific gateways or routers to a certain extent. So, the first job of the web server is to take the HTTP request and read the cookie and get the user token out of it. Once you have the user token, and it does a few other things with geographic info, the IP address, and certain contextual information, you pretty much want to shard that request as quickly as possible, because then you're going to take advantage of your L1 caches. The other thing that the web servers do is they are implementing the protocols of our partners. So, like I said, your browser requests are obviously coming through as regular HTTP requests, but the requests that we get from RTB networks can be anything. Sometimes they're just raw HTTP, sometimes they're XML, sometimes they're protocol buffers or JSON. So that tier of web servers is able to translate that and then drastically simplify the API underneath it. The other thing that we do is once you get past the web server, so when the web server is talking to what we call the ad server, you're not talking HTTP anymore. You're talking sockets, RPC, and protocol buffers. So protocol buffers is it's a serialization technology that Google actually open sourced. It's structured data, but because both the client and the server side have the same schema, the schema is not sent in the packet, so it shrinks the size dramatically. I think what we found in a lot of our serialization is that oftentimes the metadata is larger than the actual data, because you have so much numeric stuff. If you've got a 15-character tag name in XML, you'll find 80% of your XML is just the metadata. The actual stuff that's in there is tiny. So protocol buffers do a much better job of minimizing the size of the packet, but also they transmit in binary, so you're not encoding numbers as text, and it does a few other things along the line of minimizing the number of bits. So if you've got if you want to send the number 5, for example, it doesn't use 4 bytes to encode that. It'll just use 1, and then we'll encode the length later on. Right. So one other thing that we use is Guava. This is the example that I mentioned earlier. So caching is extremely important to us. We live by the maxim that RAM is disk and disk is tape. So nothing can ever hit a disk in the course of serving a request for a banner ad. So as a result, your ad server basically doesn't use the disk drive hardly at all once it's booted up. All of the user records are kept in memory in multiple places, and serialization to disk is taken care of on the back end asynchronously, and it's primarily for disaster recovery. Right, so then the next tier down is the caching tier. Biggest product or biggest open source product on the market is Memcached for caching. It's a perfect example of using the right tool for the job. It does one thing exactly. All right, I'll say it does 2 things. You can read from it and you can write to it, and that is it. Everything is key based, so it's just a distributed key store. It doesn't even do clustering. It's just a service written in C. You start it up, and you've got a binary protocol you can write to, and you send it a blob of bytes with a key, and it saves it. And when you come back later with the same key, it returns the same thing. It is as fast as it could possibly be, and doesn't have any other feature set. So it's fantastic for what we do. I'll compare that to some other products. So Terracotta is trying to make a lot of money in the same space with a commercial product, but it does also serialization. It does replication, which, as I mentioned, is the most evil thing in the world. And it has a much richer feature set, but it's also 500 times slower. And it is an extremely complicated product to get up and get working in your environment. Memcached doesn't have any of these interesting features. You can't even cluster it, but we don't care because we've already partitioned our data. We sharded when we were coming into the ad server, so we already know which Memcached server to talk to, and all the extra clustering is useless to us. It's just added complexity. So then the next tier down, persistence. So, as I mentioned, we do eventually write things to disk when we get around to it and we're bored. For that, we use Cassandra. We're actually in the process of replacing Cassandra with HBase, which is a little bit newer and seems to be getting a bit more industry support. But they're both, kind of similar products in that they're key stores. But in contrast to Memcached, they're actually writing to disk. So HBase is backed by Hadoop. It's basically a key store API on top of Hadoop. So you get to take advantage of all the scaling that you get with Hadoop, but you get much better performance for key store-based lookups. But it's very efficient at getting things on and off of disk, which is, again, that's the problem we're trying to solve there. So, we've kind of, we've taken a look at, what we need to do. We need to get things very quickly, and we need to be able to save large amounts of data to disk. A lot of products will do both of those things for you, but by splitting that up into two problems, you can actually solve both problems much faster than if you tried to use one solution that did both. I've also noted that we do use a relational database in a very limited sense, but when we do, it's always Postgres. A little bit of a historical note. So we've been doing this for like what, 7 or 8 years. We've been doing this much longer than Cassandra, HBase, or Project Voldemort, or I think even the notion of NoSQL has been around. So when we first started, we were actually using Postgres to work as a key store. And we still have that Postgres-based key store in place, and we're still using it because we actually have had a hard time finding anything faster. Our kind of homegrown Postgres solution actually outperformed Cassandra by a little bit, which was an interesting result, but it did work that way. However, you'll see that the way that we are using Postgres is very strange. It's not the way that you would normally use a relational database, and because we've optimized it so much, you actually get pretty decent performance as a key store. But ultimately, we are expecting HBase to outperform both of them, and the other kind of aspects of it, are that it it'll scale a lot easier, and some of those extra features we actually will use at that level. So then two other bubbles here. So sort of in parallel to all of these, you've got a web services tier, and then you've got monitoring and management. So I think I mentioned Nagios, OpenTSDB, and OpenNMS are all tools that we use that are very important. But we also do a lot of web services. So the way that we control the ad server is with a lot of big, messy business logic code. That's a little more conventional. So by splitting that into a web services tier that's separate from the ad server stuff, you can actually take advantage of a lot more libraries. You can use richer feature sets. You can give programmers an environment that they're a little more used to, and you don't have the kind of performance requirements that you have on the right-hand side of the screen. So that kind of architecture has actually served us fairly well. So two of the tools that we use that I like a lot, something called Enunciate, which is it's a Java-based tool, but it's purely static, and it generates web service stubs for you. So it's almost, or it essentially is sort of a compiler or a code generator. Once you run through Enunciate, and it's all based on annotations, once you run through it, you have a bunch of Java code, but you're not using any Enunciate libraries anymore. 5 minutes? Okay. And then CXF is another sort of web services framework that that has helped us out a lot. Yeah, and then the last piece. So, as I mentioned, the web services stuff is not as performance critical. But the way that we make sure that it's not performance critical, or that our web services tier doesn't have to scale to the same extent that the rest of our stuff does, is that we use a web cache called Varnish. So we have one web cache in each data center that is very high performance, and we put the web services stuff behind it. So when you've got 500 ad server components, pounding away at the web services interface to get their configuration information, it doesn't take down this much less efficient component because 98% of the requests don't actually even make it. They get, they get served by the web cache and sort of save that last component there. All right, so with that, I'll wrap up. Thank you for your time. Any questions? I think we have 3 or 4 minutes left. Sure. We do, in terms of, I don't know how to quantify it. I think we've made, I don't know, maybe a half dozen of our own modifications in the last couple of years, so not a lot. Much more often what we're doing is we're emailing or posting requests to the owners of that project and getting our features put in there. So Enunciate is actually a great example of that. I think we've gotten 3 or 4 features added to Enunciate in the last 6 months on request. And just sort of the nature of open source projects, while anyone can contribute, there's usually 3 or 4 people that that everything goes through, and unless you're writing a very large amount of code, it's often easier to just shoot them an email and say can you add these 2 or 3 lines of code, it would make my life easier, and they're usually very accommodating. For the most part, they're just thrilled to know that somebody's using their stuff. Anything else? My pleasure. Mm-hmm. Yeah, we do quite a fair amount of that. That's mostly on our side. It's not it's not something that's really reflected in the overall architecture. But yeah, the ad server will take a bid request for a particular user, and certain aspects of the decision-making process will be cached with a TTL. The basic one is, a lot of things we'll decide once per session. So kind of the way it works is that you'll have a user that's kind of tied to multiple companies that they've, registered with, or they've, been browsing at recently, or they have something in their shopping cart for. And we'll kind of roll over those. If we don't have anything available for any given company, we'll kind of blacklist that with the TTL. So we'll only check that once per day, for example. Other aspects of the, the solution, we'll get a little more fine-grained than that. But it always sort of has the same sort of shape. We're going to make this decision now. We've got the user in memory. So subsequent, requests while they're in memory, are going to continue to be in memory. But we know that this decision is going to last, X number of minutes or X number of hours, and we're not going to revisit that until that expiration is up. Yeah, we've kind of gone, we visited both extremes and then we landed somewhere in the middle. So the first edition, you know, everything was sort of done offline, and then you just, when people came, they picked up the message that they had. Then we went to the opposite extreme, and we just sort of reran everything every time they showed up. Where we're at right now, we rerun everything once per session, you know, but you know, we don't necessarily recalculate everything every time. So, you know, we have this notion of TTLs, so that you really maximize performance. And you know, it's difficult. There's a lot of extra code because you have to calculate how long every individual decision is going to be valid for. But you know, we did get to the point where we knew, you know, we knew that that was our bottleneck. So we had a very specific objective, you know, when we were doing it. So it sort of paid off. All right, thank you.